This is sample 9-3, a collision at the Bolorama. So this is our first crack at a two-dimensional collision, which, like I said before, it's not more difficult. There's just more to it. We're going to have to deal with both dimensions. And for some reason, they throw this other concept in there where we have to figure out the factor, how much faster the ball is moving than the pin, rather than just plugging and checking numbers. But there's value here, so let's do it. So you can see in the picture on the left, the bowling ball is starting with an initial velocity and the pin has no initial velocity, and we're going to figure out what happens after. So I'm going to call object 1 the pin, and I'm going to give that a mass of m. And mass 2 I'm going to call the ball, and its mass is 3.5 times the mass of the pin. Now you could have called mass 1 the ball and mass 2 the pin, and it was 1 over 3.5, but I try to keep the factors positive if possible. Doesn't make a difference. Okay, the initial velocity of the pin is 0. It's at rest. Okay, the initial velocity of the ball, we're just going to call V2I for now. So now I'm going to draw a picture of how this works. And even though I tend to think of the bowling alley lane as a vertical problem, I have more trouble doing the math that way. So I'm going to turn this into a horizontal problem, and I'm allowed to do that. Here's the ball, V2I, right? Here's the pin initially. Oops, it wants me to draw something, but I'm not going to. Here's the pin initially. Now, what they tell you, just after collision, the ball moves on a path to the left of its original direction, and the pin shoots off to the right. So here's my imaginary continuation of the ball's initial velocity. So after this collision, the ball's moving to the left at a 10% angle. So I've got to sort of tilt my head a little bit and say, okay, well, this way's to the left, V2F, and this angle is 10 degrees. Now I know I've drawn that angle way too big, but I'm going to label it so I'll be good. The pin scoots off to the right at 60 degrees. So I'm going to try to do a better job here. Here's V1F, and this angle is 60 degrees. Okay, so my drawing is not perfectly to scale, but I'm in the right quadrant, and this gives me an idea of how to start. So the question they're asking is the pin moving faster or slower than the ball, and by what factor? So what we're really looking for here, well, let's just talk about what we're looking for. We know from conservation of momentum that the total initial momentum is equal to the total final momentum. So this is, for the initial condition, just the ball, and for the after condition, ball plus pins. Okay, but I can't just plug and chug numbers because I've got to balance my components. So I'm going to have to flip back and forth between these two pages, but let's do it. So for momentum in the x direction, okay, initially the ball is moving in what we'll call the positive x direction. Let's call that positive x and that's positive y. So my initial momentum in the x direction is just m2 v2i. The ball is only moving in the x direction, so we can just write it that way. Now, after the collision, we have a little bit more to do here, because our pin, which is v1, or object 1, is moving this way, and our ball is moving this way. But the x component of the pin's momentum is just the mass of the pin times the x component of the pin's velocity. And so the x component, v1f x, for another subscript, is just v1f cosine 60, right? So I'm going to put that here. m1 v1f cosine 60 degrees, right? Now let's deal with, whoops, wrong way. Let's deal with the pin's final momentum. V2f in the x direction is v2f cosine of 10 degrees, right? Both of these are positive because these are both, v2f is a first quadrant vector, v1f is a fourth quadrant vector. Both of them have positive cosines. So I'm going to add plus m2 v2f cosine 10 degrees. Okay, so this is our conservation of momentum statement for the x direction, right? Now let's do our conservation of momentum statement for the y direction. Is there any initial momentum in the y direction? And the answer is no. The ball is moving only in the x direction, and the pin's not moving at all. So I'm going to put a big fat 0 there, and that's always a good thing if you can get a 0 somewhere. All right, now let's look at the final y momentum. Okay, now I need the y component of V1, okay, is going to be V1F sine of 60 degrees, okay? Actually, if we're going to use a full 360 here, that's the sine of 300 degrees, because we need to make sure we get a negative sign there because the y component there is negative. And then up here we have V2Fy is equal to V2F times the sine of 10 degrees, right? And that's positive, which is what we expect. So here we go again. M1 V1F sine 300 plus M2 V2F sine 10 degrees. Okay, so what we really have here is two equations and two unknowns, which we could solve. Well, actually, we have more than that. We would need one more piece of information to actually get numbers out of here. But since we have this 0 here, it's going to allow us to do this. It's going to allow me to say negative M1 V1F sine 300 equals M2 V2F sine 10 degrees. Now I can, and what that tells me is that M1 V1F sine 300, with a negative sign, divided by M2 V2F sine 10 is equal to 1, right? Now remember, what we're actually looking at here is how much faster is what's the ratio of speeds between the pin and the ball? So what we're really looking for here, and I'm just going to write it in red, we're really looking for this relationship here, right? And I can kind of pull this out here, right? And I can actually solve for this. I'm going to split up this kind of disgusting fraction into this, minus M1 over M2, V1F over V2F, and then sine 300 over sine 10. Because there's a lot I can actually plug and chug here, because remember that mass 2 was 3.5 times mass 1. So I'm going to scoot to one more page. I apologize. All right, so this is, since M2 is 3.5 times M1, then this first term can be negative M1 over 3.5 M1, that's my first fraction, V1F over V2F, which is again what I'm most interested in. Then I can do sine 300 over sine 10, which gives me almost exactly negative 5. All right, to 3 sig figs, it was like 4.98 and then a round up, okay? So I've got just a ratio there equals negative 1. Okay, that negative 1, let's see, sorry, maybe I don't need the negative. Nope, I've got the negative here, so I don't need it here. All right, so back again, sorry. This factor equals 1. Okay. So I can solve for the ratio of final speeds of the pin to the ball. And what I get is 0.70. Sorry for this extra mark here. Right? So I get the ratio of speeds is 0.7, which means that V1F is equal to 70% of V2F. Right? So the speed of let's see, which one's V1F? M1 is the pin, okay? I've always forgotten that by the end of the problem. So the velocity of the pin is 70% times the velocity of the ball. So let me write this. The velocity final of the pin is 70% of the velocity of the ball. So what we did here was we used conservation of energy in 2 dimensions. And your first response is always like, oh God, this is extra work. But what it does is it gives you an extra formula. And so we'll do a little bit more. They don't make you solve systems of equations on the AP Physics 1 exam, but they do make you set them up sometimes. And this is kind of what they did. So we'll do more of this in class. I'm sorry for droning on for 10 minutes. I hope that was helpful.